I have some representative parts here, and we're going to be basing this on a 6CL6 tube, which I don't have shown, but because we have a transformer that I've gotten from the junk box that has a 6.3 volt filament at 2 amps and a 115 volt secondary for the high voltage, I think that's an appropriate transformer for the project. Again, it's going to be a little bit lower power because that transformer is half the voltage on the high voltage that we had on the other one. So what do we have here? 6CL6. Let's see what we got in this little package. 6CL6. Yes. Beautiful. That's what we'll be using. So let's take a look at some of the parts. You'll want to collect these parts. This is more than you really need for this, but I want to show you examples of parts. Obviously you need the transformer. You're going to need some electrolytic capacitors. Here's a pair of 450 volt capacitors. These can be anything between 20 and 100 microfarads. So you're going to need some resistors. You're going to need some terminal strips. I've got an octal tube socket shown here. We're not using an octal tube, but the cool thing about an octal tube socket is you can put crystals in it. And look at this. I've been able to put 2 crystals into an octal socket. Therefore, I could have a 2-channel transmitter. That would give me 2 AM channels in the 10 meter band. Pretty cool, huh? You're going to need crystal sockets otherwise. You'll need an output connector. You're going to need a microphone input connector. You're going to need that microphone transformer, the step-up transformer. This is a miniature one that I found. Here's your tube socket. We should probably add a fuse. As far as the on-off switching and the switching from RX to TX, I like using a 2-section rotary switch, so we could have a control like off, on, transmit, something like that. Off, on, transmit. That'll take a 2-section rotary to do that. What else we got? Oh, the bypass capacitor, just standard discs. The 2 coils, the 2 tune circuits, the one for the tri-tet cathode circuit and the one for the output circuit. They can indeed be slug tune coils. If you can find some nice slug tune coils, either paper, phenolic, or ceramic, they will work fine. I'm going to try to use some of this mini inductor stock. So let's talk a little bit about the tune circuits, the cathode tri-tet tune circuit as well as the output tune circuit. These, of course, in the article used slug tune coils. You can use slug tune coils at this low power, no problem. But if you use air wound coils or toroid inductors at these frequencies, they'll work fine at this power level. You can tune either with the slug or you can tune with variable capacitors, various types of trimmers or other capacitors. So you might find a lower cost solution on these inductors. So that's the basic set of parts to build this thing. Of course, there's other things needed like the on-off switch, the power cord, and things like that. But there's a basic pile of parts to get started in the project. So here is the notional layout. And I'm trying to put this transmitter on a chassis that's probably half the proper size. This chassis was available, but you can see now that I've made a miscalculation. A lot of parts to fit on a small chassis like this. So you really would need one a little bit larger than this to do the job right and to make the wiring easily. But let's go through it. On the left we have the power standby transmit switch. In the middle we can put our crystal holder. On this end, the microphone jack, whatever it is. I am going to be using a push-to-talk microphone with this transmitter. Now with a push-to-talk microphone, I'm going to need 6 volts to run a relay And this is just a notional relay. The relay I'm using will be enclosed. It'll come off the side here. It needs at least 3 contacts. One contact is basically for transmit, to apply the voltage so the thing transmits. One will be to switch the antenna and receive ports on the back. Okay, built-in TX-RX switching. That's a nice feature. And then the third contact will be for a mute switch, and that'll probably be just a wire coming off this thing going into the receiver to mute it on transmit. So any standard 6-volt 4-pole double throw type switch that you might find probably will work for this. There is a chance of arc over with the relay approach, but hopefully we can get through it with no trouble. You can see the power transformer's way off to the left here, out of the way. The tube's right in the middle. Microphone transformer here. Oscillator components in this section. Output components in this section. I've got place for a fuse over on this side. So that's the layout of the simple one-tube transformer. So it's not looking so simple anymore. There's quite a few components, quite a few holes to put in this chassis, and it's going to be a little bit challenging, the wiring. That's why you like to put things on all the outer surfaces. That way all of the contacts are facing inward. It is a 3-dimensional problem to wire something this complex in such a small chassis. So that first inductor, the one that's used to resonate the cathode of the oscillator, can be wound on just about any slug-tuned coil form. I think I'm going to use this one right here. It has a slug, it's a paper, just a waxed paper type form. I'll just drill a hole in the aluminum, stick this through, and maybe just hit a little bit of epoxy around the top. Bang, done. Wind the coil down towards the bottom of the form so that the slug can be completely out and then go completely in. Yes, there's some plastic type adjustable coils like this and larger that would work very well at, between 10 and 15, 20 megahertz. You'll need about 20 picofarads and probably only about 15 turns on there. We'll get that straightened out. But any of these forms, and it really doesn't matter about the powdered iron core, it's going to resonate. And we will check that with the grid dip oscillator to make sure that it's resonating in the range that we want before we mount it. Now, can you use a toroid like over here? Yes, you could use either the orange, or the red or the yellow type toroids, but you will have to use them in conjunction with a trimmer to bring them on frequency. So let's wind up that first coil. Okay, we have our handy GDO, gate dip oscillator. And I say gate dip because this is a MOSFET oscillator instead of a tube. If it was a tube, it would be a grid dip oscillator. So first thing we're going to do, we have our 15 turns of number 26 wire on our coil. And I put a fairly low value capacitor across it. It's an 18 picofarad. So the first thing we're going to do is put the slug in so that it is at least just partially into the coil. We don't want it all the way in the coil, but we want it down far enough that it's having some interaction. That should be fine right there. Okay. And then we'll use the GDO to try to find the resonant frequency. I've got the coil in there that goes from around 11 megahertz to 25. That's our range that we're interested in. So let's turn that on, and got the meter so that it's it's in the linear region. So then we'll put the coil close to it, and we're going to look for a dip. Looks like we got a good dip at 14.2 megahertz. This is where you declare victory. Again, this is my first attempt at winding the coil, and we're right in the range. So let's prove it to ourselves by putting the slug in all the way, or at least a little further in. And looks like I can go all the way down to 13. Let's take it all the way out, or at least pretty far out. Again, we'll try to get this dipping going here. There it is, up at 25. So probably a 22 puff cap, 18 puff cap, anything like that will work fine with this. Now a different core might be different. This slug that's in there looks like it's possibly a ferrite core and not a powdered iron, but it wouldn't make much difference. And that's going to be our cathode tri-tet resonance circuit. Okay, we did our thing with the adjustable coil. Now let's try winding the cathode tri-tet tuned circuit on a toroid form, and this can be a yellow or a red type form. Both of those are powdered iron forms, and that means they don't have a lot of inductance when you put turns on them. So I stuck 30 turns on there to start with. So toroid circuits are notoriously difficult to dip, and I found the best way to do it in a quick and dirty manner is to put the leads on a little bit long and form kind of a circle. And this is going to give a way for the dip oscillator to at least have a chance to couple to the toroid. The toroid, remember, has a self-shielding action which keeps the magnetic field confined within the toroid. It makes it very difficult to draw energy out to get the dip to occur. So let's tune here. Not seeing anything, sorry. Get you down on the meter. Let's see if we can get a dip. Oh, there's a dip. Pretty high Q too. 18 megahertz. A little over 18 megahertz. That's a good sign, actually. That tells us that an ordinary trimmer, like this 0 to 35 puff trimmer, against that is going to be fine to set the frequency. So again, it's just a powdered iron toroid with about 30 turns on it, and we're going to be using a simple trimmer, and that will be one approach at doing this. The other, of course, the powdered iron or ferrite slug approach. So we have the powdered iron slug approach, or ferrite, whatever you can get your hands on, just as long as it resonates at the frequency between, say, 12 and 15 megahertz. And then the equivalent circuit using a powdered iron toroid and a trimmer. Okay, yes, it is starting to look a little bit like what we would call a clown car. A clown car being a vehicle that's much too small for the occupants. In this case, the occupants are a lot of parts, and we're trying to put them on a very, very small chassis. Probably half the size we should have used. But let me just show you some of the features of this complete 1 watt DX AM transmitter for 10 meters. So when I say a complete transmitter, I mean a transmitter that has provisions for antenna switching, receiver muting, onboard power supply, and we even have a selection of 2 crystals. So this is really a complete little rig. Now you might wonder what this toggle switch is here. This guy is one of those off, on, off, or I'm sorry, an on, off, on double pull, double throw. So in the middle, power is off. Okay, power is off now. In this position, the set is on with high voltage and filament, but it's not actually transmitting. and you would use the PTT of the microphone to actuate the relay and go into transmit. In this position, it is not only on, but it is also in the transmit on position. So this is for testing, basically, or it's for a microphone that doesn't have PTT, mostly for testing. And then we have a simple toggle switch here, which gives you 2 channels. Again, we're using that old trick. Basically, we're using an octal socket. With an octal socket, we can plug in 2 crystals. So that's our poor man's crystal socket. And as you can see, I got it drilled in wrong, and I had to rotate the thing a little bit to make the crystals line up top and bottom instead of being at an angle. But that's only because I misjudged the socket and I didn't know what I was doing. So again, the 6CL6 tube is going to be our oscillator transmitter. I've got a nice 6-volt 4-pole relay. We only need 3 poles, but this one has 4. Very inexpensive, something I got on Amazon actually. I think it was less than $7 for the 6-volt relay. It even came with a really nice socket, which I didn't use. I did use a socket that I found in my junk box, so these are pretty universal sockets for these relay styles. Anyway, there it is. Now, when I want to wire this thing, I'm going to have to take most of those parts off and wire them outside the chassis. That's how tight it is in there. It's going to be a very tough wiring job. Again, should have used a larger chassis. So of course the AM transmitter needs a carbon microphone. Now the best carbon microphone, and one of the types with the most output, is the ordinary telephone carbon element found in, the old-fashioned telephone. There were professional carbon mics made for the two-way radio market, especially in the 40s and 50s. And there's even one model that I believe is still in production. It's the Shure 104C. And this is a carbon low impedance microphone. And it has a carbon element. You can see it in there. This is really a beautiful microphone. And I'm going to be putting a connector on the end of this. And then the transformer will step that up so we get enough volts on that suppressor grid to produce AM modulation. So let's talk a little bit about the carbon microphone and the carbon element. Basically, the microphone is a couple of plates that have carbon granules between them. And as you talk, the carbon granules become closer together, further apart. And this is basically a variable resistor. So as you talk, you're varying the resistance of the carbon element. Now if we have a battery in series with the carbon, and we have a step-up transformer, because this is fairly low impedance. Carbon microphones are typically between 20 and 300 ohms of resistance. You need to step up the voltage that you're producing as you talk to a high enough level to go into an input stage, such as a tube. So that calls for a microphone transformer. A microphone transformer. This is an actual microphone transformer that's used in radios like the ART-13 and the TCS military radio. And this one has a 1:41 step-up ratio. So if you had 100 ohms on one side, you would have 4100 ohms on the other. Okay, so that's a step up. This is a miniature microphone transformer. This guy also can step up. It has about a 200 ratio. That's the one I'm going to use in the radio. It's an old United Transformer microphone. It's got several impedance taps on it. This is what they recommended in the article. It's a very small 4 or 8 ohm to 10,000 ohm output transformer, like you'd find in some old All-American 5 radios and so on. You might be able to find this a little bit easier than some of these dedicated microphone transformers. But before we hook this up to a circuit, let's hook up the carbon microphone through one of these transformers with a modest power supply and a load, and let's see what kind of voltage we can produce on the other side of the transformer looking at it with an oscilloscope. Okay, the Shure 104C carbon mic is a typical hand mic for mobile use, which means it has a general restricted bandwidth of 300 to 4,000 hertz with a peak right around 2,000 hertz. And basically this is an upward slope, so it gives you a lot of talk power in the 1,000 to 2,000 hertz region where you need it for communications quality. Okay, this is typical for a hand mic, whether carbon or dynamic or electret or whatever the technology is. Now, there is one caution with the microphone. In the operating instructions, they're saying that if you're running 6 volts like we will be doing, you need a minimum of 100 ohms in the circuit, or you could damage the element. So that 100 ohms would go here if this had 0 impedance. Now this old output transformer I've got here will measure the output resistance, okay, and it's really low. Okay, it's less than an ohm. So if we were just to hook this up with a battery right to that transformer, it could damage the element. So we're going to essentially have to insert a 100 ohm resistor at this point. Now we don't want to just put the 100 ohm resistor in there as it is, because that will also be a voltage divider with the transformer. You'll lose all your audio. So you have to bypass it with an appropriate coupling capacitor. So it's in series, so it's coupling, but it's bypassing the impedance of the battery and the 100 ohms. So the first thing we have to satisfy is the resistance requirements of the element so we don't burn it up. Once we have the resistance taken care of with the 100 ohms, now we have to take care of the impedance issue, which is what we're doing with this capacitor. We're allowing the audio to come fully into the transformer with no loss, but we're limiting the resistance. This resistance limits the amount of current in the element. Okay, so that's the trick circuit we're going to be adding. I notice in their design they ignored this. I think they probably thought you were going to use a telephone element or something like that probably could take this kind of abuse. But again, not great practice. You should always check to see what the minimum resistance or current through the element is before you start to heat it up or damage it. So let me describe the setup. Basically, we have the microphone hooked up to about a 7.5 volt battery here. I've tapped this 12 volt pack at the 7.5 volt range. I've got a 130 ohm resistor in series, so that represents this resistor here, and a 47 microfarad capacitor for the bypass. So we're looking at the microphone output right now into the transformer. 1, 2, 3, 4. Hello, 1, 2, 1, 2. Let's go over to the RMS voltmeter. See if we can measure something. Hello, 1, 2. Looks like I can get about 250 millivolts RMS. And when I'm talking, normal speech, hello, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, it's around 50 millivolts peaks, maybe a little bit higher than that, 1, 2, 3, 4, 5. Now let's look on the secondary of this audio output transformer. Oh, a lot more output. Let's go back up here. Here's 3 volts. Hello, 1, 2, 1, 2. Hello, 1, 2, 1, 2. Looks like I can peak up around 8 volts RMS. And when I'm talking 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, I'm about 1.5 volts RMS to 3 volts RMS. So this transformer is a little light. The ratio is not quite high enough, I don't think, to do much modulation. So the ratio on this guy must be something like, maybe a 16 ohm to a 3000 ohm kind of a thing, or an 8 ohm to a 3000 ohm. Not quite good enough for what we're talking about. That's why they specified having a perhaps a 3.2 ohm or a 4 ohm transformer going to a 10K or a 15K. You need a higher ratio to get more volts out. So with this smaller guy, the smaller transformer has a little bit better ratio. Here we are in the 3 volt scale, and I'm easily able to talk and peg it. Let's see how far we can go. We'll go to the 30 volt scale. Yeah, I can get about 20 volts out of this thing. So I do not think this microphone has the same output that a regular telephone element would have. But this ratio transformer might be a little bit light to modulate. We shall see. So this is the Shure Carbon microphone. Hello, test 1, 2, 3, 4, 5. Testing 1, 2, 3, 4, 5. We're in the we're hitting about 30 volt peaks here as we talk. Going through the transformer. This is a microphone transformer out of the ART13. So it's just an example of a carbon mic with about 9 volts, 8 or 9 volts on it, and what it can produce through a microphone transformer into a 100K load. So that's about as far as I want to go with this second video on the little 1 watt suppressor AM modulated transmitter. So I told you that I'd gone as far as to do a 10 watt version of a suppressor grid modulated rig, and I dug it out of the junk box, stuck a tube in it just so I could show it to you. This is an 837 tube. It has a free suppressor grid, and it's crystal controlled, and this is an 80 meter setup, so we have the tuning and the loading control junk box style with this pi network output. But it's an electron coupled oscillator, suppressor grid modulated, and look what it's got here. It's got an ART13 carbon microphone step-up transformer, and it's got a bell transformer hooked up backwards to produce the negative voltage for the suppressor. And this adjusts the voltage until you get the voltage in the right range to get the best modulation. So there you go. There's a little bigger version of what we're trying to build over here. Stay tuned for the next video where we actually wire something up, start to get some oscillations out of the transmitter.